So now let us come back to previous discussion, and who will give me the definition of electric charge. So electric charge is some scalar quantity which describes something. What does it describe?
Flow of electrons.
Flow of electrons, that's something more related to electric current, which we will definitely discuss. But now we are just working with electric charge. So electric charge is scalar quantity which quantifies or describes the interaction between two charges in terms of some electric force. And this electric force can be determined by means of which law? Coulomb law. So Coulomb law tells us what will be electric force of interaction between two charges when electric charges magnitude, distance between these electric charges, and obviously electric constant, which is used in the equations, are given. So according to Coulomb law, what is the relationship between electric force, electric charge, and distance between electric charges?
Electric charge is directly proportional to electric force, and the distance is.
So probably another way. Electric force is directly proportional to electric charges, and inversely proportional to what? Square of distance between them. So, building block of matter is atom. Atom consists of electrons which are orbiting nuclei, and nuclei in its turn consist of neutrons and protons. So where we have positive and where we have negative electric charges? Proton is positive, electron is negative. So most of electrical phenomena are related to transfer of electrons, since these guys are easy to remove and transfer. However, also possible that there is not only flux of electrons when we consider electric current, but it could also be transported with ions, which are positively charged atoms. When we remove electron from atom, we know that under normal conditions there should be electrical neutrality, means number of negatively charged electrons should be equal to number of positively charged protons, and that is true for micro world and macro world in general under normal circumstances. However, if because of any impact we remove electron from atom, this atom is transformed into so-called positively charged ion, and it also carries the electric charge. In magnitude, this electric charge is equal to electric charge, magnitude of electric charge of electron, but obviously possesses an opposite sign. Okay, so now with knowing this information about magnitude of electrical force, we also need to remember about direction of electrical force. Means we, during last discussion, introduced Coulomb law in vector form. And what can we tell about that? So how we define the nature, attractive or repelling nature of electric force. Two charges with the same sign, they repel from each other. If we have opposite signs of electric charges, they attract each other. So with this information, we can proceed further. And as you have noticed last time, Coulomb law is very similar in its structure, the equation, to gravitational law. Exactly. And we know what is the feature of, I would say, unique feature of gravitational interaction. Objects can interact with each other, expose certain influence on each other without being in intimate contact. Means you don't need to have a collision between two objects or some other mechanical contact between these two objects, but there is still some force, gravitational force exerted on each of these bodies because of gravitational interaction. So similarly, we have the case for electrical force, electrical interaction between two charges. They do not need to be in contact with each other. However, there is certain electrical force exerted on these bodies which carry electrical charges. And obviously, in order to realize this form of interaction, we need to introduce so-called electrical field. So we had previously gravitational field, which is created around every object which possesses some mass, like gravitational mass. And now we need to consider electrical field, which is created around, in the vicinity, in the environment around the any object which carries some net electrical charge. Means either uncompensated positive or uncompensated negative electric charge. It obviously, every object carries plenty of electrical charges, but keep in mind that they are in balance, means they compensate each other, and net electrical charge of every object under normal conditions is equal to zero. So it does not create any electrical field. However, if electric charge is not compensated, then we end up with electrical field, and now we need to introduce and quantify it. So how we define electrical field vector, E vector, is equal to electrical force vector divided by Q naught. So how we understand this simple equation? Let's assume we have some electrical field which exists in the space where we place so-called test electrical charge, this Q naught, and can measure electrical force exerted on this test electrical charge. So the definition of electrical field vector will be electrical force vector divided by the test electrical charge. So if we rearrange this equation, and we can write now that Fe, electrical force, is equal to Q naught times E. So this is very useful equation, which gives us a simple approach to quantify electrical field vector exerted on test charge Q naught, which is placed in some point with electrical vector E. So if we know electrical field vector distribution, and obviously we know electrical charge of the test charge, no matter where we place this charge in electrical field, we will know the magnitude and orientation of electrical force exerted on this charge. And obviously here we need to take into account the sign. So we can write here plus minus. So that will also define the orientation of electrical force, because we know that it will make a difference if we change the sign of electrical charge, even without changing its magnitude. So let us consider it further on some example. Let's say we have some positive charge, Q. Let's call it source charge. So that is the charge which will create electrical field in environment. And consider some point P. Maybe a bit lower. Next to this electrical charge. So here we will place some test charge Q naught. So this will be Q naught. So if we draw a line between these charges, then we know that there will be some electrical interaction and there will be electrical force which attractive or repelling. So these are two positive charges, means they will repel from each other. So force will be in this direction. Electrical force vector. So here will be our unit vector. So we consider unit vector direction from the source to the test electric charge. And the distance between these two charges will be r. So we know what is the equation for electric force. It's Coulomb law in vector form. So let's write Fe vector. It will be equal to Ke, which is electric constant, times Q naught divided by R second power. And here we have also R unit vector. So now, according to this equation, we can define electrical field vector in this point P, which is created, so this electric field is created by source charge Q. So in this case, it will be E vector equal, again, we can write here F E vector divided Q naught, where Q naught is the test electric charge. And we will end up with Ke times Q divided by R square times R unit vector. So this is the equation which gives us a possibility to determine the electric field vector at some distance r created by source charge Q. So now what we need to highlight here, we have this unit vector r. It's oriented from source charge to point charge, or this. They are both point charges to test charge. And we also need to take into consideration electric sign of this charge. So if it is positive, then orientation of unit vector r and electrical vector will coincide. If negative, then electric field vector will be oriented in opposite direction with respect to this unit vector r. Since in this case we have both positive charges, so this charge Q, the source charge, is positive, then electric field vector and unit vector coincide. So we can draw the orientation of electric field vector here in this point P. So this will be our electric field vector. Okay, so let us consider also the other case when we have negative source charge. So this is our negative source charge. Then here is some positive test charge. This is Q, this is Q naught. And now electric force will be attractive because these are two different signs of electric charges. So if we draw here line, this will be our electric force vector, and unit vector R is the same. It goes from source charge to the point where we want to determine electric field. And now we have negative sign. So here we have sign negative and orientation of unit vector R, and electric field vector will be in opposite directions. So that's why electric field vector will be defined as shown here. So now it's oriented towards the source charge instead of going away from source charge when source charge was positive. Okay, so now let us consider a system of several electrical charges. So far we considered only one source charge. However, obviously there could be the situation when we have more charges than one. So let's consider first this qualitative example, and then we will go for some quantitative analysis. So we have two positive charges, or maybe let us make this one negative. So it will be Q1, Q2, and here is some point P next to these electric charges. So we would like to know what will be the resultant electric field vector at this point P. So we draw two lines which connect our point charges with the point of our interest in space, which is this point P. And here we have electric field vector created by first electric charge. Here we have electric field vector created by second electric charge. So you see that this is positive source charge. Electric field vector is pointed away from this positive charge. Here we have negative electric charge. This electric field vector created by negative electric charge Q2 is pointed towards this electric charge. So obviously, as a vector quantity, the resultant vector will be defined as the sum of two vectors. So this is E12, let's call it. So this is the resultant vector. So now let us consider a similar example, but quantitatively. So let us have some system of coordinates here, x, y, and we place here two electric charges. So we have some positive electric charge Q1 and some negative electric charge Q2. Here at this point P, we want to determine electric field created by these charges. So we need to add here also I unit vector and J unit vector, which define orientation of axis X and Y, because we obviously want to have information about electric field
in this point P in vector form. So let us consider electric field created by first charge, then will be electric field created by second charge, and obviously here will be resultant vector E12 vector. So now what will be E1 vector? Yes.
Point P, it's just a point, or
Yeah, it's just a random point which we pick up in space around two charges. No, it
try to make each other.
oh, so this is not about electric forces, these electric fields, and we do not need electric charge placed here. So this is just empty space. We consider any point in empty space with respect to these two charges and want to determine electric field.
Well, you said that it goes like it repels from positive charge and it attracts to a negative charge, like with the electric field.
Yes, it does, but in order to have electric force afterwards, once we determine this electric field vector, which is resultant electric field vector created by both electric charges, and then if, for instance, you pick up any charge and place in this point P, we will exactly know the magnitude and orientation of electrical force which will act on this charge placed in this point. But that will happen only if we put here any electric charge. So far we are talking only about electric field. So how we define electric field vector? And according to previously defined equation, we can write that this will be KE times Q1 absolute value divided by R1 square, and R1 square is this distance. So this is R1, and this distance is R2. So we take magnitude value of electric charge because here we multiply it by I unit vector in order to define orientation of this electrical field, because it is oriented away from point charge Q1 since it's positive charge. And then we have second contribution like to this like component of this vector, but that will be 0 times J unit vector, because electric field vector in point P created by electric charge Q1 will be oriented in parallel to axis x, so its projection on axis y is equal to 0. So now we have electric field vector created by second charge, and we can write here that this will be 0 times I unit vector plus KE times Q2 magnitude over R2 square times J unit vector. So we have our electric field vectors created by first and second electric charges in this point P. Obviously now we need to sum up them, and since they are written in this unit vector forms, it is quite easy to do analytically. So we can get the final expression for resultant electric field vector in point at point P as sum of vector E1 and E2 And that will be KE times Q1 absolute value over R1 squared times I unit vector plus KE times Q2 absolute value R2 squared times J unit vector. So this is the form of the resultant electric field vector E12 at this point P, created by presence of these two electric charges Q1 and Q2. Yes.
Yeah, must be imagine when you guys the two charges on the point. It's so bad. Because
yes, in this case, it is sure. Yeah, so that's the way how we can simplify the form in order to get the zero projections on other axes. However, if there is some angle, then you need to take into account this angle, and you will have two components of vector. But this is just general explanation how you approach such tasks. So now we know already how to determine electric field vector created by point charge or a system of point charges. So because you can add here more electric charges, and the approach will be actually the same. You will just determine electric field vectors at this point P created by each of present electric charges, and then you will sum this up in a vector form. However, there is another option when we have point electric charges placed extremely close to each other. So if that is the case, and the distance between these point charges is much smaller than distance to the point where we want to determine electric field vector, then we need to deal with so-called continuum of electric charges. And there are several possibilities for continuum distribution of electric charges. So we may have as a bulk distribution in three-dimensional space, surface distribution when electric charges reside only on the surface, and also linear distribution when they reside along some line or wire. So let us consider general approach how we deal with such continuum of electric charges. So in general, we can consider some three-dimensional body and assume that we have a continuum, like three-dimensional bulk distribution of electric charge within this body. So what we can do here, we can divide it in small volumes. For instance, this will be delta Q1, delta Q2, and let's say here is some point P where we want to determine electric field vector created by this continuum of electric charges, not just a point charge. So we can draw here some lines which connect this point P with segments of this body. And here we have something is lagging. Here we have R1 unit vector, and this is R2
unit vector. So obviously these charges, which are now defined in the small volumes, delta Q1 and delta Q2, will create some electric field vectors. So this will be this 2E1. We can call it delta E1 and delta E2. So now what we need to do, we need to divide all this three-dimensional continuum distribution of electric charges in small segments. Volume should be small enough that we can consider uniform distribution of electric charge within the small volumes and determine electric field vectors created by each of these small volumes in given point P, and then sum up all these vectors. Yes, we will end up definitely, in order to make it accurately, we want to go to the limit case when delta Q will approach 0, so we will consider so tiny volumes that electric charge enclosed in these volumes will approach 0, and that will lead us to the integral. So let us show it. So this will be electric field vector is equal, as we defined earlier, will be Ke times the sum for all charges, delta Q1 over Ri square and times Ri vector, like unit vector. So that is the general case when we consider like point charges, but as we discussed, we want to get accurate solution. So we will consider limit case when delta Q approaches to 0 of this sum, delta Qi over Ri square and Ri unit vector. And that will be like vector integral. So we end up with Ke, electric constant, which we can take out from the integral dq over r square. And here we have r unit vector. So when we have different distributions for bulk, surface, and linear cases, we have different parameters to be considered for density of electric charge. So when we have volume distribution, like three-dimensional, we consider density of electric charge rho, and that is Q, total electric charge, divided by total volume. So units for this density of electric charge is Coulomb per cubic centimeter. If we deal with surface charge electrically charged surface, then we have sigma, and that is total charge accumulated at a given surface divided by its area. So units will be Coulomb per centimeter square. And linear case, we have this lambda is equal to total charge divided by length, and units for lambda Coulomb per centimeter. So now, once we define general case, how we approach this, let us consider some specific example, and that will be electric charge distributed over some rod, and the goal will be to determine electric field vector next to this continuum of electric charge, linear continuum of electric charge. So this is our system of coordinates. X, Y. Here we have the rod with some uniform linear distribution of electric charge, let's say positive electric charge, so total charge is positive, and lambda, which is Q over L, and L is the length of this rod. So this is constant. It's not a function of position along axis X. So now let us pick up this point P. Where we want to determine electric field vector. So this electric field vector, according to the symmetry of the case and positive charge, will be oriented as shown here in opposite parallel but opposite to the axis X. So now what we do, we define some small element of this rod, this continuum of electric charges, with the length dx at the distance x from this point P. And we also need to define the position of this rod with respect to the point P. So that is distance A from this point P to the edge, left edge of the rod. So now, what will be electric charge confined in this small element dx? So dq is equal, any suggestions? So we have linear distribution of linear density of electric charge lambda. So if we multiply this density, linear density, by length of the rod element, that will give us electric charge. So means that dq will be equal to lambda times dx. So we have now electric charge, and we assume that this element is very small. So we can just determine electric field vector as it would be at point P, as it would be created by a point electric charge. So we know the equation. So for this point dE, we consider here magnitudes, because orientation comes from the sign and symmetry of the case. And this electric field magnitude created by small segment will be equal to Ke, electric constant, times dq over x squared. So electric charge over x in like distance to the point in second power. Now we substitute dq with this expression, Ke times lambda dx over x squared. And we can write for electrical field, like resultant electrical field created by distributed charge already, not just by small element, as Ke times lambda. These two terms are constants, so we can factor them out from the integral. And here we have integral. What is left? It's dx over x squared. And now we also need to define the limits of the range of integral. So it starts where we start, at this point, which is a, and and at this edge of the huh?
A plus L.
A plus L, exactly. A plus L. So that is our defined integral now. So we integrate it, we will get ke times lambda times minus 1 over x. And here will be from A to A plus L. We will end up with ke times lambda minus 1 over A plus L and plus 1 over A, taking into account this negative sign. So we can rearrange it. It will be ke times lambda, and here we have 1 over A minus 1 over A plus L, and end up with ke times lambda times L divided by A times A plus L. And what is this? Q times L, like this is this capital L. Total electric charge, which is residing on this rod, which we consider. So that will be Ke times Q, capital Q, over A times A plus L. So that is the magnitude of electric field, which is created at this point P by a uniform linear continuum of electric charge, some positive electric charge Q capital. So now we know how we determine electric field when we have point source electric charge, a system of point sources, and continuum of electric charges. Another important concept which we need to introduce here before the end of this lecture is the concept of electric field lines. So in order to simplify the graphical representation of electrical field, it was introduced so-called electric field lines. So what does it mean? So first of all, what you need to know about electric field lines, that at any point of electric field line, the tangential to this electric field line will be our electric field vector. So it is drawn in that way that the tangential, that electric field vector is tangential to the electric field line. And we have orientation of electric field lines. They are shown with an arrow. So electric field lines originate at positive electric charges and terminate on negative electric charges. So if we consider positive electric charge, then we can depict electric field lines like radial lines, which are originating from this positive charge and going away from this positive charge. If this charge is negative, we have similar case, but all these electric field lines terminate on the negative electric charge. So we need to also highlight another feature, that the density of electric field lines per unit area on cross section define the magnitude of electric field. So the larger electric field, the denser will be located to each other electric field lines. So it's not about orientation. So in this case, the density of electric field line highlight the magnitude of electric field. And now, if we take this into account, let's say we have small and large positive charge. Where will be more electric field lines coming out from these charges, for smaller or larger? For larger, because larger electric charge will create larger electric field around itself, and in order to highlight this feature, we need to draw more electric field lines around it. So the larger electric field, electric charge, the larger number of electric field lines will be depicted around it. And of course, orientation, as I mentioned earlier, originates at positive charge and terminates on negative charge. At any point, the tangential to the electric field line will give us the orientation of electric field vector. Its magnitude is defined by density of electric field lines per unit area. So these are some technical definitions of electric field lines, which you need to keep in mind. And later we will definitely operate with this concept.